This is a review of the key concepts from Chapter 3, the characteristics of the normal distribution. Part 1 will talk about populations, samples, and standardized scores. In this case, our standardized scores are z-scores. So we know already that a population is every individual in the group of interest, but we know that it's hypothetical because we just can't get every individual in the population of interest. For example, if we are looking for every individual who has say the population of interest is all the students at Diné College, we know that we can't get in touch with every one of them. You know, some of them live far away, some aren't currently registered, we just can't do it. So we use careful practices to draw a sample. If we do these carefully, we can infer back to the population. If we gather data from representative samples across a long period of time, we get some known parameters about this population that we refer to as mu, sigma, mean, and standard deviation. Our sample are just those individuals that we've chosen to represent that population, and we just use plain English language to represent the sample. In order to get a representative sample, we have to take care. We have to rely on random selection from that population of interest, which means every member of the population, or every student at Diné College, for example, has an equal chance of being selected to be in the sample. If we have like the political polls and so forth, they do usually take serious measures to get random selection. So if you are randomly chosen, they might bother you a little while to make sure you respond to their survey. They might call you more than once. And that's because they need to randomly select in order for it to be representative. Often, though, in real life, we do rely on convenient sampling, or what your book calls haphazard selection, because it's just easier. It's hard to get a random sample. And even a convenient sample or a haphazard sample can still provide meaningful information. Generally, if we do that and we're doing an experiment, we want to make sure we randomly assign people in different groups or different conditions, and that will take the place of random selection. And if we haven't been able to obtain a good random sample, then we take care to generalize only to populations with the same characteristics of the sample. Just by way of a quick example, if I am interested in college students and I decide to use a sample of college students here at Diné College because that's the students I have access to, then I would want to make sure when I conclude my study to generalize only to, for example, students at tribal colleges, or maybe even only to students at Diné College. We describe populations and samples differently. When we talk about a population, we call them parameters, and that means we're talking about the center or the mean of the distribution and the spread or standard deviation of the distribution. They're called parameters rather than statistics because they're based on accumulations of data over time where we can't go back and get all the raw information. So it's just a pattern within the population, but we can't go back and get all the raw data. Large samples are how we get population parameters, and we represent them in Greek letters such that lowercase sigma represents the spread or standard deviation, and sigma squared is the variance, but in our class we just say variance. And then mu, the lowercase mu, represents the mean of that population. Again, these are population parameters because they are tendencies over time, not based on a specific calculation in that moment. When we're talking about a sample, we call them statistics because we're calculating them right then. And same thing though, we express it in the mean, median, standard deviation, variance, and so forth. Those are the sample statistics or the mathematical characteristics of the sample that we've drawn from the population. And we use English letters. M in our case equals mean. You might have seen this in X bar in a previous class, capital X with a bar over the top of it. Same thing. We use SD for standard deviation because we've actually calculated it. We have every number involved. And your book is going to use SD squared for variance. In the past, I and other students have found this confusing, so in our class, once again, we're just going to say var instead of using this SD squared, even though it's the same thing and this is what your book uses. So we already know the importance of this normal distribution. It's so important because all characteristics in nature tend to fall into a normal distribution if we have enough individuals. A very quick example, I am looking right now outside my window at a bunch of birds. And each one of them, they're all the same time. I don't know what kind they are. They're a bunch of little gray birds, but they all, they're not exactly the same size, and some of them maybe have a larger wingspan than others. And if I were to measure the wingspan on all of them, I might come up with a mean, and most of the birds would be kind of in the middle in terms of their wingspan, but there would be some with a much smaller wingspan, some with a much larger wingspan, and if I measured enough, they would come to form a normal distribution with very few birds having a very big wingspan and few birds with a very small wingspan. So most things in nature fall into this. For example, height of women. If we gather heights of women in the USA and get a lot of information, we know that the average or the mean for that population is about 64.5 inches with a standard deviation of 2.5 inches. Another example is IQ test scores. We've given IQ tests to millions of people probably, and we find out that in general there tends to be a mean of 100 and a standard deviation of 15. And adolescent self-esteem, there's a scale called the Rosenberg self-esteem scale, and if we give it to very, very many teens, we find that on average they have a score of 32.3 with sigma standard deviation of 5.3. We can fill these scores in. For example, if we were to fill in the IQ scores, the center line represents the mean. So in IQ test scores, mu, let me get my pen here. In IQ test scores, mu equals 100, and the standard deviation of 15 means that between each of these bars, we have 15 points. So right here, we would get 115, another 15 points here, 130 here. These gray lines represent standard deviation lines. Abbreviating it in that way because we are talking about population parameters here. And we know that we could subtract the 15. We know that there's 15 here also, but it's going in the other direction. And so if we take 100 minus the 15, we would get an 85. And another minus 15, we would get a 70. And we could continue on. And we could continue this way. Someone could get a 145. It would be very rare. Remember, these are frequencies. On the x-axis, the number of individuals. Not very many individuals are getting scores this high. Not very many individuals are getting scores this low. Most individuals are getting scores somewhere in the middle here. That's what we look at this distribution. Theoretically, this distribution goes into infinity in both directions. We can have some score that would be 10 standard deviations away from the mean, and that's all perfectly reasonable within the normal distribution, but very rare to get such a score. Now, many things that we're measuring come on different scales. For example, the ACT math scores come on a scale with a mean of 20.5, and this is the ACT, and a standard deviation of 5.5. So here at one standard deviation, we'd be adding the 5.5 to get a 6. We'd be adding it again to get a 31.5. And coming down, we would have a 15.5 at one standard deviation below the mean. Remember, these are the standard deviation lines. And did I get that right here? That would be just a 15.0. And going down another one, we would have 9.5 here. So we know that those are the ACT scores. SAT math scores have a different scale. I'll get a different pen to mark it. Let's mark that in this reddish color. SAT scores have a 527 as the mean, as mu, and 107 as sigma. So we would have to add the 107. We would have 634 at 1 standard deviation above the mean. Taking away the 107, we would have 420 at 1 standard deviation below the mean, and so forth. So if we have a college trying to make admission decisions based on these test scores, they're going to have a hard time if they have students presenting different scores. And so what we do to avoid that problem is we just make a standardized scale so that every single test can be looked at on the same scale, and that scale is called the Z distribution, and mu is always going to be 0, and we just mark the standard deviations one at a time. So any score that falls here would have a z-score of 1. Any score here would have a z-score of 2. Here we would have a -1, a -2, a -3, and a +3 up here. So this is our z distribution, and we can align scores on any scales to this z distribution. So if we had a person with a score x1 equals 20.5 on the ACT, we would know that their z-score for that person is equal to 0 because it is lined up. If we had a person with x2 had a 634 on the SAT, we know their z-score is going to be 1. Let me erase that so that it's very clear. Their z-score lines up with the 1. Right here. And if we had someone with is 9.5 on the ACT, we know their z-score is going to be -2. If we were looking to see among these individuals whose math scores are the highest, even though their raw scores aren't that informative, we can see that this individual, score 2, whose score was right about here, actually had the best performance on this test. And if we added one more, let's add an x4. Let's give this person a 31.5. This 31.5 in a raw score is lower than 634, but the z-score, line here, is 2, and this person scored 2 standard deviations above the mean, so their performance is the best of all. If this campus can admit only one person, they might choose to admit this person, even though this 31.5 is not as high as 634. So our standardized scores are just an agreement of how we're going to view these, sort of the same way we all agree to measure distance in miles, weight in pounds, and so forth. We agree to measure these particular scorings with many different scales to put them all onto this z distribution with a mean of 0, mu, and sigma of 1. Another example applying these z-scores as a standardized tool, our scenario is that students took a career aptitude test. They wanted to determine what area to go into based on their talents and natural abilities. And they know the distribution of this aptitude test. They know that on average for service, the mean score, and I'm going to do a little key for this. Let's do this color. The mean score for service, we'll mark in red, is going to be 50 with a standard deviation of 10. So here we have 50. I'm marking it in red to represent service. Standard deviation of 10 means that 60 would be at this one standard deviation line, 70, 80, 40, 30, and 20. So that is the service. I don't need to write it in because I keyed it. We also know that technology, this has a technology aptitude score as well. And we know that the technology aptitude score, we will mark it in green. We know that the mu is 100 and the standard deviation is 15. So I'm marking these 130s. So if Jordan gets a 130 on the tech score and a 70 on the service score, her aptitudes are equal in both of those areas. All I'm doing here is subtracting and adding the standard deviation of 15 so that we can line these up. Now we can see that it is difficult to compare scores on these two scales because the scalings themselves are different. And so what we do is we turn them into z-scores, which always, as we just mentioned, have a mean of 0 and a standard deviation of 1. So these would be numbered out like so. And so now we can find out how Jordan's doing. So it looks like on her tech score, she got an 85, and on her service score, she got a 65. We can see that the 85 is a much higher score than the 65, but because the scaling is different, we want to use z-scores. Let's go ahead and mark her 65 on her service. 65 is going to fall right about here. And so this is her service score. Her raw score is 65. And we can see that she has an 85 on the technology score, which falls right about here. If we turn both of these into z-scores, we can see that in the case of the 85, the z-score is -1. So let's write that. And on the service score, we can see the z-score is, it's halfway between the 60 and the 70 because it was 65, and that would be equal to a 1.5 on the z distribution. And so in this case, the service score is higher than the technology score, and if we were going to give her some advice, we might say, well, you seem to do better in the service area, whatever that means, because the z-score is higher. Or we might say, well, you need to improve your technology ability so that you can do well in that area, you know, however we want to look at it. But her aptitude right now seems to be in service. So we standardize the scores. So finding z-scores and x-scores, first off, we can just look at the distribution. So if we have, first off, let's always write our z-scores on here. It's always going to be 0, 1, 2, 3, -1, -2, -3. Now we have this characteristics, 150 with the mu and 20 as the standard deviation. So I'm adding this on to go up in this direction and subtracting it to go in the other direction. 130 minus 20 is 110. 110 minus 20 is 90. We know the shape is normal. Now we need to find what the z-score would be. So if a person's individual score is 190, it's going to fall right here. We know their z-score equals 2. If their raw score x is 130, right here, we know their z-score is -1. And if we have a raw score x of 180 right here, we know their z-score is right between the 170 and the 190, or right between the 1 and the 2. Their z-score is going to be 1.5. That's basically how this works, using this normal distribution to find the z-score when it happens that the score lies right on the standard deviation. And we can do that in reverse too. If z equals -2 right here, we know that the raw score is going to equal 110. If z equals 3 right here, we know that the raw score is going to equal 210. And if z equals -1.5, it's going to be right in the middle of these two. We know that the raw score will be right in the middle of these two, 120. So just to review the characteristics of the z-distribution, first off, it is a standardized scale for measuring spread of distributions of raw scores when there are different means and standard deviations, which is almost every scale. The mean will always be 0, and the standard deviation will always be 1, and the shape will always be normal. You're ready to take a couple practice quizzes based on this information. Sometimes we have to calculate a z-score from a raw score because the raw scores don't line up exactly on the standard deviation line. Here is such a situation. We have mu of 150 and a standard deviation of 12, so 162, 174, 186, and going down, subtracting 12, we have 138 and 126 and 113. Here we have Sandra, whose score is inconveniently 160. It's not right on the line. It's falling right about here. And how are we going to deal with this? We have x1 equals 160. We can't know what the z-score is. We know it's going to be somewhere between, it's going to be approximately maybe 160. We're looking at a number that's between 150 and 162. Maybe that's what b. We can use a formula to calculate it. Z1 equals the raw score, 160, minus the mu, 150, divided by sigma, which is 12, equals 10 divided by 12, 2 divided by 6, 1 divided by 3. That's not going to be right, so let's go ahead and get out the calculator and get it correct. One of the benefits of Excel, 10 divided by 12, and we get 0.8333. So this z-score and I put that down wrong, it's 0.8333. And forgive my error here. I should have put the score that's going to be right about here. I already knew the x score was 160. I should have said the z-score was probably around 8/10 of the way in the middle there. Let's do this one with a more accurate estimate. Let's go ahead and do Jerome. His raw score is 132. So let's go ahead and find where the 132 would be. It's going to be right about here, between the 126 and 138. X2 equals 132. What kind of a z-score might we have? We're going to have a z-score somewhere between -1 and -2 and a little nearer to -1. I'm going to estimate that as approximately -1.4. And let's calculate and find out. Z2 equals 132 minus 150 equals -18 divided by 12. Let's get out the calculator and see what that ends up as. And we get a -1.5. I guess that was smack dab in the middle. Not quite where I drew it, -1.5. So that's the idea of how we use that formula. We can estimate and then we can go ahead and calculate using that formula. And we can also do that in reverse. Of a delay here while I am finding my slides again. So working in reverse, we just have a reversal of the formula we just used, which is to calculate x, we take the z-score, multiply it by the standard deviation, and add the mean. And so if we have that same distribution, the 150 with the 12 standard deviation, I'll write in a few of the numbers here. And now we have some scores here, but we have z-scores. Eleanor has a z-score of 2. It's easy for us to know that raw score because x1 just equals 174. It's right on the line. But Cordell inconveniently has a z-score of 1.7, which is going to fall right around here. So z2 equals, not negative, equals just 1.7. And what would we estimate the raw score to be? We might estimate it to be approximately somewhere between 162 and 174, maybe a little closer to the 174. Let's make it 170, and let's calculate. X2 for Cordell equals his z-score, which is 1.7, times the standard deviation of 12 divided by, adding, let's just kind of write that in dark, adding the mu of 150 and 1.7 times 12. Let's get the calculator tool out. This is the reason I'm really fond of Excel. 1.7 times 12, and we get 20.4. We'll add the 20.4 to the 150 to get 170.4. And that's close to what we estimated, so that looks good. And we can use the same formula to calculate any kind of a raw score from a z-score. A little bit of a delay here once again while I find the screen.